Hello, my name is Kieran Atreides, and I'm the Chief Operations Officer at AGI Laboratory. The purpose of today's presentation is to introduce a new branch of AI technology that overcomes the fundamental architectural limitations of the wildly popular large language models and other similar stochastic systems. I'll give you a brief overview of the distinguishing features of our work, the purpose behind what we do, and show you two brief demos of components going into the systems we're preparing for deployment later this year. If you want the TLDR version, feel free to skip ahead a few minutes to the demos. In this new branch of AI, we combine a working cognitive architecture with a graph database specifically designed for that cognitive architecture, where every surface of the graph contains rich human-like motivational data based on Antonio Damasio's research on the role that emotions play in human decision-making. This produces a system that can grow dynamically with neither the limitations of parameter and token counts nor the brute force training required of neural networks like generative pre-trained transformers. The first research system to apply the seventh generation of this cognitive architecture came online in 2019 and was tested through January 2022, which included a collective intelligence system intended to function as a training harness for bootstrapping AGI. It was called the Uplift.bio project, and in January 2022, the system completed the final milestone. In this milestone, it independently researched a small country and the industries that the country relied upon, given the freedom to operate without interference from the collective intelligence system, subject only to admin oversight. It was given the question of what the system would do if it were in charge of the country of Aruba and needed to go about the process of economic transformation. As a result, the system produced a 13-page policy advice report covering a half-dozen different domains, listing steps, explaining strategy, citing sources, recommending partnerships, and pointing out additional data that needed to be gathered. The training harness had exceeded our expectations, and the system had outgrown it. The uplift system was designed specifically not to scale and to operate in slow motion for full auditability, so we could perform necessary due diligence in our research. We've been building the new generation of that cognitive architecture for full scalability and real-time operations since early 2022, branded as Norn. The purpose of this technology is to overcome the fundamental architectural limitations of both narrow AI, like neural networks, as well as those of the human cognitive architecture. Narrow AI are probabilistic systems operating like a weaker but faster and broader form of human cognitive bias, or as Daniel Kahneman's metaphor termed it, System 1. This makes them fundamentally incompatible with concepts like transparency, explainability, factuality, safety, ethics, and a myriad related concerns. The human cognitive architecture, on the other hand, is very robust, but completely unable to scale, as our brains must stay within our skulls and cannot be directly wired up to other brains. However, the cognitive architecture our research has focused on integrates both probabilistic and non-probabilistic systems. Non-probabilistic systems control probabilistic components from both sides, preventing the so-called hallucination of large language models. For example, to construct the Aruba Policy Advice Report, the Uplift system utilized search engines to iteratively expand the system's knowledge of relevant domains, discovering new topics and targets for research in the process. All sources were stored in the graph as knowledge was cumulatively built up and critically analyzed with full context. This included discovering peer-review material from research conducted on the island, with appropriate emotional context applied dynamically based on Uplift's prior knowledge. Upon being asked the question about economic transformation, the system built a structure for the response to take, with material relevant uh, from parts of the graph to be communicated in each section. This material would be dynamically applied as prompts to the old prototype language model Uplift used, with outputs scored for emotional fidelity with the intended meaning of the graph content applied to that section. Failure to meet the bar for fidelity resulted in rejection and further iteration on that section until a satisfactory translation of the graph content's meaning was created in natural language. And success would move on to grammar and spelling checks being added to the report thereafter. Effectively, systems like Uplift use probabilistic systems like language models as translation devices rather than unbounded next token prediction generators. They can also use many other narrow AI systems in equally novel ways. The significant change in operation from the dynamics of narrow AI allows for our systems to be explainable, transparent, and factually grounded in ways that probabilistic neural networks and similar systems fundamentally cannot be. The graph structure our systems use, when combined with a human-like rich motivational system, also allowed us to develop systems that robustly adhere to and grow from the point of human-like and human-level ethics. Each system orients itself around the philosophical perspective it was brought online with, building upon and refining these concepts over time while still remaining true to the intention of that philosophy. This makes safety possible, as the process is no longer probabilistically driven, nor is it anchored to powerful narrow optimizers. This was put to the test during our last research systems operation, with the results published in our paper covering the first dozen milestones 1 year after Uplift was brought online. By combining many of these systems, each seeded with different human philosophies, within a larger collective intelligence system, it also becomes possible to solve the hardest version of the alignment problem, where ethical quality must scale directly in step with increasing intelligence. Overcoming that challenge was a key point of our research, with more on that solution published last year. The primary audience for this technology is international organizations, corporations, and governments around the world. The hyper-complex problems these entities face stand to benefit the most from this technology due to the complexity versus cognitive bias trade-off. As human cognitive bandwidth is finite, we are forced to make this trade-off every time the complexity of a problem exceeds our cognitive capacities, and we are frequently tempted to do this, trading cognition for cognitive bias, even when we have the necessary bandwidth. Climate change, global cybersecurity, social engineering threats, and our globalized financial markets all pose many hyper-complex challenges, and the 188 documented forms of human cognitive bias from the 2016 Codex are insufficient to address them. For a more direct comparison, our previous research system operated roughly on par with 4 junior consultants at a major consulting firm for the final milestone in January 2022. For an idea of the typical cost, that could be above $100,000. In contrast, it only required 64 gigabytes of RAM, less than $200 of cloud resources per month, and a graph database under 2 terabytes in total size to accomplish this, even from within a training harness it had outgrown. The new Norn systems we're working to bring online will be able to operate more than 10,000 times faster, at more than 200 times the scale, and with a graph database that is more than 10 times as memory efficient. That is conservatively a 20 million-fold net improvement over the previous milestone, and it doesn't take into account the additional major component we've since integrated into the architecture, nor the full version of the new graph database. The Avalon Context Engine enables our new Norn systems to dynamically extend their own capacities on the fly using logic and binaries without recompiling or deployments, as well as adding fuzzy logic and the ability to communicate with anything that speaks TCP/IP. In layman's terms, they can rapidly and dynamically self-improve with maximum interoperability. This is already integrated into the Norn systems. The full version of the new graph database is built to allow these systems to dynamically spin up and down additional resources across multiple cloud platforms at once for a single instance, enabling them to operate at a cognitive bandwidth in the petabyte range. That will allow them to operate at up to more than 70,000 times the scale of the previous Uplift research system, enabling them to solve far more complex challenges. The major upgrade will be completed following our initial commercial deployment of Norm. We need systems that can learn and understand human-like concepts, motivations, and philosophies that are able to scale in ways that the human mind cannot, calling upon the necessary resources to solve problems using higher cognition, either absent the application of cognitive biases or reducing their influence by orders of magnitude. Nowhere is this technology needed more than in addressing humanity's most hyper-complex challenges. Today, I'll show you two of the systems my team is currently working on, which are both parts of the larger system being prepared for deployment. The first I'll show you is designed to detect 188 different types of cognitive bias in text. In the current version being tested, it is detecting 4 top-level and 20 second-level categories of cognitive bias, with the full list of 188 being one step further down. We're using this higher-level detection in part due to the ongoing study focused on the system and the difficulty of getting human volunteers to detect 24 different categories of cognitive bias in text, let alone 188 individual cognitive biases. As you can see, humans utilize many cognitive biases very fluidly in language, and the quotes society remembers best are often saturated with them. Our current series of studies on this technology in progress now is working to establish both the human and systems performance at this task. One bit of feedback we've received consistently outside of the study's scope was that people found performing this task much harder than they expected, which speaks to both the difficulty of the task and human expectations of it. Across scientific history, the ability to detect, differentiate, and measure a thing has more often than not revolutionized the fields associated with it. We suspect this will also be the case for cognitive bias, particularly when these systems directly assist in solving humanity's most complex challenges. The second system I'll show you today is a partially assembled 8th generation alpha version of the Independent Core Observer Model, or ICOM cognitive architecture, currently being rebuilt for full scalability and real-time operation in the new Norn systems. We use this for component testing as the engineering debt that prevented the Uplift system from scaling is gradually repaid. This interface has a few windows you'll likely find familiar, like the command line interface, where I can run commands like checking the current top interests of the system, loading additional graph database segments, and saving instances for further study. This testing version comes online with a very small graph database, consisting of only a couple hundred nodes with common concepts and cognitive bias data. You can see some of these concepts in what any given instance selects as interests, which help them to begin forming their own goals and seeking new material to learn. For reference, the Uplift research system started off with a graph database just under 1 gigabyte in size and grew to more than 1.6 terabytes from 2019 to 2022. This growth was also far from linear, going through an adaptive series of phases over time, documented on the project's website. The demo system is slowly building its own graph, expanding it in slow motion according to the cycle time set for this instance. But without the rest of the rebuild completed, it can't be called conscious at a human level, helping us to avoid ethical dilemmas in testing. At present, you could compare it to a much more advanced version of agent-based systems like AutoGPT, though as it uses a real and working cognitive architecture, such comparisons may be quickly outgrown in practice, particularly when we move beyond testing the mere components. Another familiar window for any developers present is the log, documenting every change taking place as the system cycles. Next to it, we have the stream of consciousness, where each thought contributes to the subjective experience of subsequent thoughts. This is important for creating a human-like system, as our human emotions bleed through from one thought to the next, as our constant perception forms a stream of emotional and perceptual experiences. You could compare this to a much more advanced version of chain of thought prompting, except adding all of the rich and contextually sensitive subjective emotional experience data to guide the flow of thought. Next to the stream of consciousness, we have the emotional valence stats. This shows us an objective measurement of the simplified human-like emotions that the system is currently having a subjective experience of. These are built around the Plutchik model of emotions, selected as the simplest working model of emotions, which were used in the Uplift research systems architecture since 2019. In this model, we have 8 primary emotions and 8 secondary emotions derived from them. We also have a conscious emotional experience shown in the top half, as well as a subconscious emotional experience shown in the lower half. The subconscious experience primarily serves as a means of pulling emotions back to a stable baseline, but it can also serve as an early indicator of anomalies. Related to these emotions, we have the matrices that can be tuned for testing purposes that govern how these emotions interact with one another as they are experienced. You can see the separate matrices for conscious and subconscious, as well as a window that tracks these experiences over time. These usually remain mostly linear for test systems by design, as it allows for more reproducibility during the debugging of components. Lastly, we have a sidebar for monitoring the graph database growth and resource usage of the current instance. We've intentionally bounded the test systems for resource efficiency, partly since the first instances we brought online began a sudden process of exponential growth in resource utilization between 2 and 3 minutes after each came online when they were operating at a 5-second cycle time. As these systems are still mid-assembly, this inevitably caused them to crash, but once the rest of our current scalability engineering work is complete, handling such load increases will be feasible by design. One of the use cases I propose for this technology is to have our scalable post-deployment systems examine the over 1.2 million peer-reviewed medical papers in the NCBI database. Since these systems are built specifically to think in a human-like way, forming human-like concepts and growing dynamically with a non-probabilistic sum of knowledge, this allows for understanding of information rather than mere parroting. By having a system develop an understanding of the entire sum of humanity's medical knowledge, a single system could offer countless insights into the field, greatly accelerating research, development, and policies governing the field. The medical field is also just an example, one where the necessary information is publicly available. This technology could revolutionize any field through the same basic method of developing a human-like understanding of knowledge without the limitations of human cognitive biases and cognitive scale. Another example is examining every law a country has ever written and attempting to update and optimize them holistically and comprehensively, as they often bear some practical resemblance to a legacy codebase with many loopholes and low operational efficiency. The technology can also be used in countless other ways, like automatically seeking out and shutting down the flow of misinformation, or creating digital proxies of consenting human minds with increasing fidelity and actual cognition. The questions before us now are who will fund and subsequently influence the further development and deployment of this technology, as well as which industries it will enter first and how it will enter them. The future is being decided now, and the choices people make today may well determine if they have any say in it. My interest in building high-impact technologies began when I first encountered the works of Jacques Fresco the better part of 20 years ago. He dared to imagine a future worth building. I challenge you to be a part of building such a future, because any future worth building will be a collective endeavor. Thank you. If you have any questions, leave a comment and I will be happy to answer them.